Okay, welcome everyone to this meeting of the virtual CICS user group. I'm Trevor Eddles, I'm CEO of TechEd Limited. We're a mainframe consultancy, analysis and authoring organisation, and we're the people responsible for the content on the virtual CICS website, where we produce the newsletters, etc. And you can find our website at iteched.com/virtual CICS. And we also look after the virtual IMS US user group and the brand new virtual DB2 user group. So if you've got anyone who uses those, tell them to join our group. Anyway, let me just allow a few more people to join. Right. Let's run through the agenda for today. Most of the meeting then is going to be taken up with a presentation. And today our guest presenter is Larry Strickland. He's Chief Product Officer at DataKinetics, and he'll be discussing making the case for developers to use in-memory tables. And a copy of the slides from this presentation should be on the website later today. And if you missed our previous meetings, you can download copies of those presentations from our website too, and you can listen again to the whole presentation. There's a link on our resources page. Following Larry's presentation and any questions you have for him, we'll move on to the latest CICS news and the latest CICS related articles. And then I'll give you the dates and times for the next virtual meetings. So that's the plan for this meeting. I'm anticipating that it will last for just under an hour, something like that. Let me just let some more people in. Okay. As I just said, today's presentation is from Larry Strickland. Larry is the Chief Products Officer at DataKinetics. For most of the past 30 years, Larry has built his technology career by making innovative technology simple for the end user and helping them solve their most challenging issues. In fact, Larry's long-term work with IBM and the mainframe community at large has earned him the honor of being recognized as an IBM champion. So if anyone's got any questions, if you can type them into the chat and I'll ask Larry as we'll go along. But otherwise, I'd like to thank Larry for being with us today, and let me stop sharing and you can start sharing.
Thanks, Trevor.
Okay.
So let me know when you can see that.
Yeah, I can see that now. Okay.
So good morning, good afternoon, depending on where you are. It's a pleasure to be here and talking to this group. I do like to support as many of the mainframe initiatives as I can, which was one of the reasons they made me an IBM champion, which in one way of looking at it is a great honor, but it does also get me into conversations I wouldn't otherwise have been in, and I really do enjoy many of those conversations. There we go. Okay, so topic today is making the case for developers to use in-memory tables. And Trevor's already introduced me. I'm the Chief Product Officer at DataKinetics. So why are we looking at in-memory in general? So the primary reason is because there's getting more and more of it, so we can take more and more opportunity to take advantage of that memory. So many of the concepts that I'm presenting today have actually been around for very long periods of time. They're getting more and more frequent use, largely because more and more memory is being available and the opportunity to leverage more memory to speed up applications or reduce elapsed time or whatever the objective is becoming more common. And why we want to do in memory versus going from disk? Well, it's basically several orders of magnitude we're looking at here. So the difference between accessing data from disk is going to be in the order of 1,000 times slower than accessing something from memory. Approximately, there's a whole bunch of other things that come into play as to what may differ those numbers, but generally you're going to see that in-memory access is going to be much faster. We talk about milliseconds and microseconds, so we talk about a factor of 3 orders of magnitude. Sometimes that order of magnitude is much higher. So that extra time taken to take data from disk can slow down an application significantly when we're typically talking about wait times. It can also increase the amount of CPU required to actually do the processing required, which is another downside, because the CPU actually not only slows down the application, it also increases the cost often, depending on which licensing scheme something is running under. Why? What's happening in the background? There's a whole bunch of steps that are involved in retrieving information from disk. I don't even pretend to understand all of this stuff because I try and avoid it if at all possible. But it is quite complicated. There is actually a white paper. If anyone's interested in going into this, there is a white paper that actually goes and explains all this stuff. Generally, there's a lot of steps. There's handoffs to other systems. There's transfer to subsystems. There's waiting for the actual disk itself to spin to the appropriate position where the disk is, where the data is. So there's a lot of things that have to happen, and there's a lot of things that have been done to optimize this. So there's buffers in there and there's channels in there that actually help retrieve that data faster. Still, it is a lot of effort to retrieve a data. So where we can avoid this, obviously, we can accelerate things. So I'm going to talk to a number of different in-memory use cases that developers should be aware of. Whether they can take direct advantage of them or not is a different matter. But there are many techniques that can be used to leverage memory to speed things up. So things I'm going to be looking at today, caches and buffer pools. These are well known. In-memory tables, and when I look at in-memory tables, I'll be looking at indexes and sharing those in-memory tables, which can again bring in different workloads that may be eligible to use those. I'll talk about fast insert. I'll talk about in-memory sorting. I'll talk about temporary tables. I've managed to get shared tables in there twice. The other one is look at whether I should be looking at large or small tables. So first technique I'll talk about is a buffer pool. So the idea behind a buffer pool is buffer pools or caches, or they're called various things, but they're actually all essentially using the same mechanism. So if I've got an application represented by an agent that wants to retrieve data, the idea is it goes and looks in a piece of memory called a buffer pool or a cache, and it sees if the data is in there first. And if it's not in there, it's then going to need to go and retrieve that data from somewhere else. So ideally, if I've read the data in the immediate past, I keep a copy of it. So if it's required again, I can just grab it from the buffer pool, and I've removed a lot of that IO processing that I'm really trying to avoid. So basically the way it works is the agent goes, sees it if it's in the buffer pool, or if it's in the buffer or cache. Again, all these terms are almost equivalent. The agent would then direct access that from the disk, and in doing so, copy the disk into that memory area and then retrieve it from there. The advantage of this is if any other agent needs to get that data, or that same agent needs to retrieve that data again, it's going to have it in memory and it's going to be much faster. So this is great, but buffers themselves have some challenges. So one of them is it's necessary to work out when the data that you've copied into memory becomes invalid. So there's a number of techniques for this. Obviously, if anything changes on the disk, then anything that's copied it to memory also has to invalidate what's in memory. So that is a big challenge in making sure that happens in an appropriate speed, such that you don't get any inconsistencies in your data. The other thing that may invalidate the data is that it's been there for a while and nobody's accessed it. And the reason for doing that is we actually want to free up this memory so that we can copy other data into that memory block. So we need to have mechanisms in place to invalidate that that block of memory so that we can free it up, we can use it for something else, hopefully copying other data into memory that's going to be accessed in preference. So one of the other things that many buffer pools or caches will use is a prefetch process. So the idea behind a prefetch process is often when data is accessed sequentially. So we're going to get row 1, then the next thing we're going to look for is row 2, and the thing after that we're going to look for is row 3. So the advantage of the prefetcher is when it goes to disk, it may not just get one row, it may get many rows, because often reading a block of data is just as fast as reading a small amount of data. So the prefetch will actually read in a block of data. And by doing so, it's got the next couple of data retrievals already in memory, and we're gonna accelerate things very quickly. Prefetchers can get smarter than that too. They can anticipate what's coming, and they can actually pull all that information in. And again, the whole objective is to accelerate things. So very similar techniques. So DB2 buffer pools, they work on this particular principle. The packaging cache, which is a component of DB2, is also using this. Instruction pipelines in the CPUs are doing this. This is in the actual physical cache of the CPU. It's doing that. It's trying to prefetch. It's trying to line everything up. It's trying to get these multiple hits for data that's already been pulled into the cache. Data pipelines are similar, vSAN buffers. This is a very common technique. It's used a multitude of different places to accelerate things. I make the observation that the primary goal of all this is really to reduce I/O. We're looking at removing that amount of time an application may have to pause while a subsystem goes off to disk and collects data and comes back. So the primary goal of all this really is to reduce I/O wait time. Depending on how it's implemented, it may be able to reduce the CPU, but as I said, the primary goal here is to reduce the I/O wait time. One of the things, I forgot to add a slide in on this, one of the things that developers need to be aware of is that often the management of these things are done by the systems or the applications themselves. This is outside the scope of the developers. So managing the DB2 buffer pools is often going to be in with the admins. Setting up the vSAN buffers is going to be the sysprogs. So often these mechanisms are being done automatically in the background. Developers do need to be aware of it, because this might be something that helps them out in the performance of their application and not actually require any changes to their application. So this is the first in-memory technique that I would talk to, which is buffering or caching. So the next one I'll talk to is in-memory tables. So in-memory tables look an awful lot similar to these buffer pools that I just went through, or awful lot of these cache. So the idea here is we're going to assign a block of memory to a table, and then we're going to take data out of a data store. And I'm not calling it a disk, I'm calling it a data store. This could be vSAN, DB2, IMS, or just a flat file. It doesn't matter what it is, but some data storage element is going to be used that's persistent. And you're going to take a copy of that and you're going to put it into memory. And then that same agent that would have gone into the buffer pool, this time it's going to go into an in-memory table. The big advantage to the developer of using an in-memory table is this infrastructure, this technique is completely within the developer's control. How they manage that in-memory table is within their control. So similar with buffer pools, you have this challenge of what happens if the data changes. So we've made our good copy of the data in this case, we've made it in memory. So now we know our good copy is in memory. So if we make a change, this change is going to be made directly in memory, which is great. That's a very fast thing to do. Application can move on very fast. We do have the challenge of we need some other process that's actually going to monitor the fact that there's been changes there and make sure that change is persistent somewhere and somehow. Such that that data, if there's a failure and the memory is wiped for whatever reason, we haven't lost that data change. So where buffers have to worry about invalidating data, in-memory tables have to worry about what happens with data changes. And I speak to a number of different accounts on a regular basis, and I swear every single one of them has come up with a different approach to managing those data changes. So there are a variety of ways this can be done. The more common one is to just monitor that memory. If it changes, replicate those changes through to the store. Sometimes the store is kept as the master, and if there's any changes in the data store, that's just replicated through to the memory. So those are common ones, but there's as I said, dozens of other techniques that I've seen used here. And I won't be going into any more of those in this presentation. One of the other things you can do with in-memory tables is you can start to share these tables between different applications. The challenge with sharing it between different applications is now you have to worry about read-write locks, because you could have one application trying to do an update while another application is trying to do a read, or worse, you can have two doing simultaneous updates on the same row. So as a result, you need another structure. This structure is also kept in memory. It's a series of read-write locks that actually control how many applications, or how applications are able to access that table or update that table, so that we keep our data consistency between the different applications. So these read-write locks look awfully similar to the read-write locks you might put on a database that's using a disk for storage. But it's the same idea. It's just applied in memory. And again, one of the big advantages of doing this all in memory is it's fast. It does have its disadvantages, failure being one of them. But putting that in memory can give you some extremely fast options. So then once we've got a table in memory, we want to access it. We want to access it as fast as we can. And this is where table indexes come in. So when we look at a traditional index that's going to, for an on-disk system, typically this index is going to be quite large, because we're going to have both the key value and the location within the table where that key exists. And that's because the index has to stand on its own. We don't necessarily have an easy way to work out whether when we're searching this index, whether we found the right key without having the value of the key there. We do it a little differently within memory tables. So again, we've assigned a block of memory for the actual table. So this is just the rows of the tables. And if we have a key within that table that we want to sort this table by, we can then, rather than doing anything with the key itself or the table rows, we can create another block of memory. And that block of memory is nothing more than an ordered list of addresses of where those keys are. So when we're doing our test as to whether we found the right key, we just look in this location and we know exactly where in the table we're looking to find the key, and we can find it. So because it's all in memory, we can do this very fast. It's just simple math. If we know where the start of the table is, and we know how long each row is, and we know where the key offsets are, it's just a simple calculation to work out where it is. And therefore we can search this table extremely fast. And if we've got that index where it's sorted the rows, then we can do a binary or sequential search very fast. So there are other mechanisms as well, but that's the gist of it. The other nice thing about doing it in memory is we can create an alternate index quite quickly. If for some reason we want to search on a different key, or even use a different search mechanism within the same key, we can just create an alternate index. And one of the things we've found is that creating these indexes is actually faster than reading them in from disk. As a result, there is no real advantage in storing these indexes, just the definitions of how are they defined, so that we can then recreate them on the fly as we need to. And this can be very powerful. And I'll come to an example later on where this alternate index actually makes a substantial difference on on application performance. The other thing we can do in memory that is very powerful is an in-memory sort. So the most common sort algorithm that's used is what's called a merge sort. And basically the way this works is you take a list. So I've got my list up the top here, and I need to sort that. So what I do is I split this into smaller and smaller problems until essentially I've got just 2 elements to compare. So I'm just doing one comparison. I'm doing a whole bunch of comparisons. So I do that comparison. So I've now got ordered subsets. And then I recombine, and as I recombine, I only need to consider one element at a time, as I'm basically filtering these sets back into each other until I come up with my ordered list at the bottom. As you can see, there's a number of interim steps along the way as I do this sort. So it is very efficient to do this in memory. If I can do this in memory, this is going to be extremely fast. And again, all I'm sorting is the address of where the actual key is. So it doesn't matter how big or small the key is. I'm not moving the key around at all. I'm just copying the address. So I'm using typically a 31-bit or a 64-bit address. That's the only thing I'm sorting. So I'm sorting and changing the location of that to tell me where my key is and where I'm pointing to it. So again, this is a very fast mechanism. If I can do it all in memory. If I can't do it all in memory, I have to store some of the interim results on disk or somewhere else, so that I can then continue with the rest of it and then go back and retrieve that and then continue down the sort. So any sort algorithm, almost any sort algorithm, I should say, all the ones that are familiar and certainly fast ones, are going to benefit from having more memory. So the more memory you can give to that sort algorithm, the faster it's going to be and the more efficient it's going to be. And if you do it just by sorting addresses, even if the ultimate goal is to put that sorted list onto disk, then you've got a list of addresses and you just need to retrieve from each of those addresses and put them to disk if that's the plan, right? Obviously, most of the cases we're looking at, we're leaving it in memory. So once we've got that sorted list, we're good to go. We don't have to worry about anything else. So I know that DB2 obviously improves its use of in-memory in almost every release. So in DB2 version 12, it basically gave you the option to allocate a lot more memory to its in-memory sorting process. So it expanded the number of nodes you could use in a sort tree from 32,000 to 512,000. So there was this huge availability of being able to do sorting by using more memories. So you did have to take work to go in and actually give DB2 the extra memory to make sure it could use this. But when you did, the results were quite spectacular. So if you were between their old size of sort and their new size of sort, being able to do it all in memory, there's a 75% reduction in CPU. So this was just spectacular. So if you can allocate the right amount of memory in DB2 and you've got sorts that are occurring within this range, you're looking at a 75% improvement. So that's a huge speed gain in memory sorts. So in-memory sorts, where they can be done, should be done. They do take more memory, but given the amount of CPU they give you back, that can be a huge gain. However, when you apply that to generic workloads, so these are some generic workloads IBM has, even though individual queries may have had spectacular results because those individual queries fell within that sort range, overall, there isn't necessarily anywhere near that same level of gain. And again, it's because which workloads fit within this new mechanism that's going to be useful. Another thing, another way we often index stuff, and again, I'm talking about in memory, but this applies to any table that you're looking to index, is what we call a hash index. So the idea of a hash index is you put the key through some kind of function, and that function does a bunch of non-linearity things on it, and it throws in a bunch of primes. And I've got an entire presentation on why that's useful. But the advantage of this is it takes a key and it appears to take that key and just map it to an address slot. So in here, I've got a table with 4 rows in it. I've created a hash index, and I've said the index is going to have 8 slots. So my function is going to give out a number between 0 and 7. And I put the key in that function, and it spits out the number, and that number is the slot that it's going to go into. The advantage of this is I really don't search. I'm just implementing this function. And so when you've got particularly large tables, hash can be substantially faster than other methods, even binary, which is obviously a very efficient search algorithm. Because this is a direct calculation versus a sort, it can be extremely fast. Empirically, we've noted that if we're less than 10 rows, actually, it's not even worth doing a binary search. You're better off just doing a serial search. If you're between 10 and 100, then binary search is faster, because this function that is used to calculate the key in a hash is quite expensive. And then when we go above 100 rows, it actually turns out that hash can be much faster. So we've worked with deployments where there was millions of rows in the table, and clearly the hash was extremely fast. There are a number of different hash algorithms that can be used. Some are very efficient in avoiding collisions, because obviously my function could spit out, for the 2 different keys could spit out the same address slot. I've got to deal with that, which is a challenge. So there are different hash algorithms that can be used to maybe make that more efficient or less efficient, or cheaper to calculate or more expensive to calculate. But that's relatively well understood what those are. This mechanism is a very fast way to index those tables. And again, this should work for both stuff on disk and in memory. I'm obviously referring to the in-memory aspects of it, because that's what I'm more familiar with. So examples of in-memory tables. So DB2 has a concept of in-memory table. It also, once you've fixed a table in the buffer pool, it's obviously clearly in memory. However, DB2 is also bringing with it all the structures that are necessary for it to be a full database, and having all the support on disk that DB2 implies. This is quite different from some of the pure, well, I'm calling it pure just to differentiate from these hybrid systems, which is what I call DB2. Pure in-memory table solutions such as our Tablebase and IBM's OCTA products. We also see in-memory tables crop up in different languages. So COBOL has the concept of an in-memory table. And we've also come across a number of companies that built their own homegrown in-memory table managers, or in-memory table systems of some kind. So we do know there's quite a few different examples out there. It is important to differentiate between some of these in terms of performance. So our own product, Tablebase, this has been compared directly against DB2. All we're looking at here is inserts or reads from a simple table. We're not looking at any of the other database features, and no way do I even begin to suggest a Tablebase as a replacement for DB2. But for certain workloads, it can augment performance quite significantly. And again, it's because it's giving those in-memory techniques to the developer directly. So Tablebase is going to be in the order of 20 times fast for a random read, which is often where it gets used more than anything else. And it's that speed or less CPU requirements that actually you can see huge gains in particular workloads. Another in-memory technique that's often used is fast insert. So one of the challenges applications can have, particularly when there's many applications trying to log data into a data store of some kind. So again, this could be vSAM, DB2, or whatever. The challenge is that if both applications are trying to update, or multiple applications are trying to update the same table, they have to get an exclusive lock in order to do the update. And so these applications are competing with each other quite heavily in order to write out this data. So depending on the scenario, it might be applicable to say, well, how about rather than doing that, we actually give each application its own dedicated space to write its new rows to. And that way there's no conflict. You don't need that dedicated write lock to do it. So these inserts can happen quite independent of each other, and as a result, there's no conflict. And as a result, this does speed up quite a bit. You'll hear different dedicated tables, dedicated pipes, dedicated pages. There's different ways of describing this, or channels is another one. But this is the mechanism and how it works. Is each application has its own typically memory block where it gets to write its new rows to with no conflict. And then there's another process that exists. And that other process exists is actually going to suck those rows out and actually do the actual storage and the permanent storage. So the typical applications for this where you've got regulatory compliance. So where you need to track accesses to something, and actually all you're really doing is just journaling what was done or providing traceback scenarios so that an audit can be completed as how this result came up. This information can be inserted without competition, and as a result, much faster. Some of the challenges is obviously if there's competition, if there's no competition between these, it's difficult to index this at the same speed you're doing the insert. So the indexing has to be able to catch up. Which means you can't retrieve the data immediately. If you insert it, you can't retrieve that row that's just been inserted until the indexing is actually caught up and is aware that that row exists so that it can be retrieved. The other challenge you have is you can't have different applications inserting rows which have the same key, and as a result, you get a conflict in the keys. And again, there's many mechanisms to do that. So again, looking at DB2, it actually introduced what it called fast insert 2 algorithm in version 12, and that is exactly for this purpose. It's using memory structures to let applications insert rows without competition, but it has that challenge. There are workloads, constraints on what you can put there because of this inability to be able to read back that data straight away. Another area where we see in-memory tables used a lot is what we call temporary tables. So a temporary table typically is only going to last for a short period of time, hence the word temporary, I guess. So an application may create an in-memory table. It may do that because what it's trying to do is sort that information or store it for a short period of time, or hand that information off to another application. So it creates it in memory. It can use a fast insert mechanism, so avoid indexing, insert all the data, then generate the indexes if required. It's doing that. It makes very fast write, very fast indexing. And then, of course, you've got this data in memory. So if you need to sort it, you can do that sort and then retrieve it. And again, it's from memory, so it's very fast. So these temporary tables can really accelerate performance. I do have a customer example of that. So this is a customer we've worked with for a large number of years, and we're asking them how they were using some of the technology that we helped them out with. And this was the example they gave. So they had a COBOL program that used a COBOL internal table to search through a table. So that table, I think it had 1.25 million rows in it. And had 4 different searches, and it was those 4 different searches that became the important part, because that application took over an hour to run. So to speed this up, we took that exact same internal table and we copied it into the pure memory technology, such that we could create multiple indexes. And now searching those 4 different ways across those 4 different indexes became exceptionally fast compared to the original implementation. And that application went from over an hour to under a minute. So it's about a 98% reduction in amount of CPU required, simply by taking advantage of this alternate index structure that's available. So again, a great example, very fast, of how a temporary table might get used. I'll often get into discussions about which tables are the best tables to put into in-memory technology. And it's not small or large. It's actually the tables where each individual row is read most frequently. And I'll give you an example of that. So again, drawing from some real world examples, we were faced with a long running batch job. That long running batch job, what it did is it accessed a table of transactions from the previous day, and it would step through each one of these records one at a time to reconcile the previous day's activity. It's actually credit card related. And somewhere in each one of those records was a pointer. And that pointer basically explained what type of credit card was being reconciled. Essentially, that was a join out to a number of different tables that had about 100 rows in it. I think there's about 100 different credit card types. So each one of these tables had about 100 rows in it, give or take. Some of them might have 1,000 rows in it because they had multiple records per credit card type. Doesn't matter. There was a collection of smaller tables that were needed to be accessed for every time you access that main record. And this particular long-running batch job was becoming a problem because it was taking 8 hours to complete. So when we looked at it, we said, okay, well, each record in that big table is probably only being read once or twice. So the gains you get from putting that into memory to read once or twice, well, if you only read it once, your effort of putting it into memory is just the same as putting it directly into the application. So you're not actually gaining anything. But these other smaller tables, each record was read tens of thousands of times. So now you've got this massive gain return. If you take the effort to put it into memory and now you're going to read it thousands of times, you're going to get gains on every single one of those reads. And if you multiply it by the number of tables, it's even bigger again. So what we were seeing is it was these little tables that actually had the best opportunity to accelerate this application, where this big table really didn't need to be dedicated to memory. And that was good news. And the really good news is because the amount of memory required wasn't as significant. It was just these small tables that needed to be replicated into memory. So again, this is the result. So this reconciliation batch job was taking too long. We moved those smaller tables, or helped the account move those smaller tables into memory, used a pure in-memory technology techniques to get access to that, and reran it. And that 8-hour batch job now completed in under 15 minutes. Most of that was actually elapsed time, so a 97% reduction in elapsed time. There was significant reduction in CPU; it was around 90%. But the big concern for this particular situation was, in fact, the elapsed time. So we improved that quite significantly. This is another example. Only explaining to Trevor, sorry, I lost my file, I had to rebuild it. So this one doesn't have the animation I was hoping to have in it. This was an example we found in an account, a bank, that they had a short running batch job. This was a very short running, didn't run for long at all. And what this batch job, but it ran very often. And what it did was it opened a file, a vsem file. It read attributes from the vsem file, a random number of attributes from the vsem file each time, and then it closed it and then went off and did the rest of its processing. So in this case, this was using an awful lot of CPU and causing an awful lot of wait time. So working with that customer, we showed them how they could, rather than rely on this file, they could actually use an in-memory table. And they removed this, open the file and close the file, and just had the reads. And what we saw from our results is that we saw a 75% improvement in the CPU requirements for the reads, but obviously we removed 100% of the open and close, so we actually saw 100% less CPU for the opens and close. So between these two, we actually saw a 93% reduction in the CPU required for that particular job through the course of the day. And in this particular system, that accounted for more than 24 hours of CPU saved in an entire day. So again, a spectacular result. And also a huge reduction in elapsed time as well. So, very good result. So, getting into the last part, I'm going to talk a bit more about cache on the mainframe. So every time a new chipset comes out, typically these cache, the core cache and the level 3, 4 caches are actually being increased in size. So we've got the opportunity to get more and more stuff in there. And the good news is the closer you are to the CPU, the faster it can be retrieved, the faster the application can run, which is all good. So ideally getting stuff close to the top of this pyramid actually gives you a much faster runtime. Oh, sorry. And I'll note that most of your data or your database that you're going to be using on a regular basis is actually going to be sitting down at this this disk level. And we've already discussed that the memory is going to be 1,000 times faster than this, right? So when we do buffering or caching, what we're doing is we're basically taking some of that data and moving it up into the system memory. And that once we're in the system memory, we know we can access it faster. So these techniques, what they're doing is they're pulling this data up closer to where we want it. When we get into some of the in-memory technologies, one of the things we've noticed is if we're using small tables and we're keeping our applications, the racks that are using those data small, and that's not always possible, but if we can do both of those, what we see is we see that both the data and the application that's using it, and one in the instruction stream and one in the data stream, are actually being pulled closer. They're actually being pulled up into this level 3, 4 cache. So when we start to see second order effects, we actually start to see accelerations beyond what we were expecting. And it's because we're fitting more and more into these cache. And when we're designing some of this in-memory technology, we're actually really concerned about the length, the application side or the code set size, so that we can get everything we need to in the single cache line. And by putting everything in a single cache line, it executes much faster. It has the downside of it never actually pauses, so other applications can interrupt. But there are other techniques for dealing with that as well. Yeah, so by getting everything into that cache line, we actually see things move very fast. So again, when we see these second order effects, they're starting to show up more and more because we're starting to see more and more cache available to actually trigger that second order effect. So that's been really good. So one of the questions I always get asked, so I anticipate that and I put a slide in to directly address it, is what about IDAA? Where does IDAA fit in all this? So IDAA, my quick summary is it's really good at taking long-running queries and making them run very short. Because they're long-running queries, typically they don't run very often because that would bog down a system to a certain extent. But take those long-running queries and make them run very fast. This is at the complete other end of the spectrum compared to an in-memory table. So an in-memory table, it's looking to take something that normally only takes a very short period of time and runs even quicker. But what's important is if it only takes a short period of time, to make it worthwhile, you need many, 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 many transactions or many, many attempts to retrieve that data before it becomes a big enough chunk to actually worry about a different technique for handling it. So, that's my quick summary of IDAA. I can go into more details if people want to at some other time, but yeah, that's my quick summary on IDAA. So in summary, I think I'm right on my time there, Trevor. I talked about various in-memory techniques that can improve performance. And again, you have to worry about the workloads and what that's going to be. So I talked about buffers, in-memory tables, in-memory indexes, both using in-memory sorts or with an address only sorting the addresses and hashes, fast inserts, temporary tables, small tables, hopefully, and shared tables.
Okay, yes, fantastic. Has anyone got any questions? Because if you do, can you type it into the chat, please? We'll give people a minute or two to do that. or maybe you've explained it absolutely thoroughly and there are no questions.
I find that hard to believe, but sure.
No, it's can't see any. Okay, well, if anyone does come up with any questions later, you can email them to me, and I'll pass them on to Larry, who I'm sure will get back to you fairly promptly.
Sounds
Okay.
good.
Yeah, no, I will move on then. Well, Larry, thanks very much for that. That was really interesting. That was lots of stuff I wasn't really, quite aware of. I sort of half knew some of it, but yeah, I hadn't seen it all packaged up nicely like that. So that was really good. Thank you. And
Thank you.
because we're a virtual user group, please assume that you're getting a virtual round of applause now. So thank you very much for that. That was really interesting. Okay, let me just share my screen again. Right, let's go on. News. Yes, well, you probably know that on the 11th of January, IBM announced the CICS beta version 6.2, which they say enables development teams to create powerful mixed language applications while allowing the operational teams to manage those applications from a single point of control. So that seems quite interesting, maybe worth having a play with if you've got time. There's a link to that announcement on our website, of course. And then we've got articles. So we've got detect and remediate weight problems using IBM Z AmigaMon for CICS, and that's by Israel Gross, and that's on the IBM Z and Linux One community website. And we've also got this one with the longest title I've ever come across, I think. ZOS Connect version 3.0.65 now available. Call RESTful APIs from CICS COBOL applications. And the ZOS Connect operator is enhanced to support routes and ingress. And that's by Kate Bittles, and that's, again, on the IBM Z and Linux One community. So, as you can see, planned for the future, our next meeting is on the 9th of May, when we have Colin Pierce speaking again, and he's going to be discussing how to define CICS maintained data tables to the coupling facility resource manager. And then after that, on the 11th of July, put the dates in your diary, that's when Israel Gross, Principal Solutions Advisor for Rocket Software, will be discussing problem analysis and performance tuning for CICS. Okay, I wanted to mention the Arcati mainframe yearbook. I know a number of people from the CICS user group actually completed the survey. So just to let you know, the brand new Arcati mainframe yearbook is now available. It's a PDF and it's completely free to download. So if you're looking for that, it's on the itech-ed.com website and /Arcati. You can download each of the chapters or you can download the whole thing. So as well as the annual user survey, there's an up-to-date directory of vendors and consultants. There's a resources guide, a strategy section with papers on mainframe trends and directions, a glossary of terminology, and a mainframe evolution section. So yeah, probably worth having a look. Now, on the Broadcom community area. So Broadcom is one of our sponsors, and it's created a virtual CICS user group page for us in their community platform. So it's a place to share ideas, collaborate, ask questions, and connect with the Broadcom's mainframe experts as well. It's kind of like their version of a listserv, I guess, but I know from time to time people send me questions to see whether I can help with that. Now we've got a place where you can do that kind of thing, so that'll be great. The URL on screen is where to go. Click register, that's in the upper right hand corner, and once you're registered, just go to the virtual CICS user group page and click join. I'm going to be using it to share information about upcoming meetings and stuff. So other information will be there. So it might be worthwhile having a look, see how that works out for us. And just a reminder that you can keep up to date with what's happening in the world of CICS and on the virtual CICS user group website by following us on Facebook and Twitter, and there's even a LinkedIn group as well. Now, the URLs for all of those are on our website, so I'm not expecting you to write them down now. And we've got a YouTube channel, which is where the recordings of all these sessions go. If you tweet or Insta or anything, then the hashtag to use is hashtag virtual CICS. And if you do use social media, then of course we like likes. So if you're on Facebook or Twitter or whatever, then like us. That would be great. So that's all for this meeting of the virtual CICS user group. Can I thank you all for attending? Thanks to IntelliMagic, Broadcom and DataKinetics for sponsoring our user group. And of course, I'd particularly like to thank Larry Strickland for his presentation today. So that's it. Thank you all very much for joining the meeting, and I look forward to seeing you all on the 9th of May. So thanks and goodbye. Goodbye.